The Xilinx MicroBlaze microcontroller system that we are using in our SoC exposes an I/O bus to the outside world. And this I/O bus that is exposed to the outside world is different than its internal bus, which might be a lot more complicated. This I/O bus is a lot simpler and it allows us to communicate with different I/O cores. What we will do is we will take the I/O bus, connect it to the bridge, and that particular bridge will translate it to our own custom built bus, which we call the FRO bus. But before we actually build the bridge and understand how the bridge actually should operate, we need to understand its internal signal in here. So when you created the MicroBlaze microcontroller system, you actually checkboxed in here and you said enable I/O bus. And this is what allowed the IP catalog actually, or the wizard, to create this particular bus and those signals. So if you take a look at these signals, and we can figure out what signals are exposed to the outside world by looking at the instantiation module or the instantiation template. So if you go to Vivado, this is how the vanilla SoC is constructed. Of course, everything's already included. So if you go to the IP core, you're going to see that the CPU is here, and I have a couple of templates. One is for VHDL, one is for System Verilog, or actually this is Verilog. So if you double click on it, you will see that this is the instantiation module that the wizard has created. And this instantiation module has a couple of interesting signals. A couple of signals that are clock and reset, and the rest of them are actually the I/O bus. So if you did not click on that, you will not see any of the other ones in here. So let's go and take a look in details about on these signals. So specifically what we have is we have the I/O, all of them are called I/O, so I'm just going to call the name. It's actually an address strobe, and it's actually a 1-bit, and it is from the master to the slave. And its purpose is to let the slave or the I/O core know that the address that is actually on the address line is actually good, meaning it validates it that the processor has finished putting all the bits of the address line on the address bus. The next one is actually the actual address, and because we're dealing with the MicroBlaze microcontroller system, it's a 32-bit. It's a 32-bit byte addressable in here. Okay, so it's different than our subsystems and what they use in here. So we're going to use this particular factor actually in the translation. Again, there's another signal in here, and this is called a byte enable. Because we're dealing with the byte addressable, we do have about 4 bytes that we're writing into that address, or we're actually accessing, whether you want to access byte 0, byte 1, byte 2, byte 4. So we have a 4-bit in here, and probably it's actually 1-hot encoded. Then we have a read data, and this actually comes from the I/O core to the master, which is actually the processor, and of course it's 32-bit because we have a 32-bit processor. This is the actual data you're reading from the slave or from the core or from the external I/O. And then we have a read strobe. So the read strobe is actually related to the read signal. So when the processor actually issues it, it's actually a master to slave. When the processor issues it, it indicates that it wants to read something from the I/O cores. Then we have an I/O ready, and this actually comes from the I/O core, or the slave to the master. And this is just to tell the processor that the I/O core has finished what you requested. Whether it's a read or write, it just finished. So the processor knows that the I/O core is done. So if you think about it now, I'm going to pause a little bit before continuing. The I/O ready actually and the address strobe can be used to handshake between the processor and the different I/O cores. So the processor can assert the address strobe to tell the I/O cores outside of it that the address on it is ready, so you should continue or do something. When the I/O cores is done, whether it's reading or writing, it actually issues a ready signal, and the processor knows that it's signal. So it's actually using handshaking. If you continue looking at these signals as well, or these wires, you'll see that we have a write data. This, as the name implies, is just the data you are writing into the slave, which is also 32-bit. And again, you have a write strobe, which instantiates or issues the write command. Okay, so this is how this signal is. Again, if you take a look at the instantiation module or template in here, you will see that I have only a clock and a reset, and the rest of them are all included with the I/O bus, because we didn't include any of the UART or the other GPO or GPI. We didn't include anything, so nothing is exposed to the rest of the world because we're building it from scratch. Okay, So let's take a look at a little bit about the microcontroller system for the MicroBlaze timing diagram. Similar to the F Pro, we'll explain it with read and write. So let's start with the write. In the write, you will see that the processor does the following. It put the address it wants to write to, which core, which register within the core, and so forth. It puts the data that it wants to write, okay, on the address, on the data bus, on the write data bus, or the part of the bus that actually deals with the write data. And also, if you are utilizing or just writing one single byte of these, you can actually put them right here, and it will figure out whether you're writing to byte 1, 2, 3, or 4. We're not utilizing this because we're just writing 32-bit at a time. And then once all of this is done, it actually issues a couple of signals. One of them is actually to tell the cores and everybody that is listening, that the address that is actually on the address line is actually correct, validated, and I want to write. So it actually raises the right signal here, which is the right strobe. And it raises all of this. The microcontroller system is actually doing it on this rising edge of the clock, and we'll see that it takes some time. There's of course different delays, and after a certain period of time, the IO core respond with IO ready, which means I did get your data and I wrote it to my internal register, and the processor knows at this particular moment the write has been successfully done. So let's move to the read in here. So the read is very similar. First, you put the address you want to read from the IO cores external to the processor. Next, you actually tell me that the address is valid. And last one, you actually issue a read strobe signal in here, which issues the command for the core to tell it I want to read something from your internal registers. So what happens is there's a little bit of delay, of course, between here and there and so forth. And it appears, yes, so there's a little bit of delay, but anyway, after a certain period of time, you'll see that particular that there are some data that appeared on the read data bus, and the core actually issues an IO ready. That means the data on that data bus, or the data that I put on the read data bus, is actually ready for you because I'm done putting it for you, or multiplexing it and routing it to you. And at this particular moment, the microcontroller actually samples this data, and it knows that this data is what was saved in the IO core or in the slave. So what we need to know in here is the following. So for the write command, it took about 1 cycle to write, but it doesn't have to, because I can actually take a lot more time to write into. And the same goes with the read. And in here, I'll see in the read that the command to actually start writing was started in here, or particularly in here, because this is where the active edge of the clock, whether it's here or here doesn't matter. What matters is the following. It took 1, 2, and the third one actually is when it happened. So on the third active edge of the clock is actually when the read actually happened. So it took 3 clock cycles. So our internal bus is not taking 3 internal clock cycles. It's actually just taking 1. So this handshaking between going like, hey, the address is ready and I'm waiting for the core to actually reply, it might create in our system, because we're doing something from scratch, it might create some problems where one of the cores might just hold all of these lines forever, and it won't release the address, it won't release everything, and the processor will be just waiting for this ready signal, or I'm ready signal. So what we'll do, we'll not adopt this, because if we did adopt it, we're gonna have to figure out what to do in terms of the handshaking and what to do with it. And if you're not doing the handshaking protocol, you will have, for example, to come with something like of a time, like if the handshaking didn't work and you just want to basically cut the line, you need to know some sort of a timeout mechanism, and it really overcomplicates our design. So we're just not going to adopt this, and we're going to assume that everything finishes within 1 clock cycle. Okay, and it does not for the processor, but for our subsystems after the bridge 8 wall. And worst case scenario, if you know that this is something that happens, you can just insert some FIFO buffers.